My name is Mike Bangham. I was the deputy lead systems engineer. While assigned here at Marshall, I actually was supporting the Langley team. And by the time we actually flew, I was the chief engineer for the systems team, for the system engineering team up there at Langley. So I was heavily involved in most of the aspects of the program right from its inset. So I was involved in the initial planning all the way through, obviously, the launch. The risk is that during recovery of the SRM that we would get a nose down condition that would cause excessive loads on the drug chute cover and would interfere with its deployment. So we were worried about the structure actually failing during nose down reentry conditions. That was due to the CG and CP, center of pressure, center of gravity, being relatively close to each other. There were a lot of uncertainty associated with where the center of pressure was and the center of gravity. Obviously, the center of gravity is we have to predict for an empty vehicle. We can measure it for the full vehicle, but we have to predict it analytically. Initially, our first cuts at that showed as much as a 12% failure rate. Failure rate being nose down. At about the CDR level of the program, we had we were carrying the 12%. That was exposed to the agency. That was taken all the way up to the highest levels of the organization within the agency, and acknowledged that it was a analytical estimate based on a great deal of uncertainties that we had at the time. Those uncertainties being the aerodynamic environments. This is a very complex separation that was going on in terms of aerodynamics. You have one very large body pulling ahead of you, and that causes the wake, the shock layers, to actually propagate outward, and the SRM is buried inside that wake. And once you start rotating, when you fire the tumble motors, it's that SRM is going to process outside into those shock boundaries, and it wasn't necessarily, we weren't that confident at that point in time of actually what those shock boundaries, what the aerodynamics would do to the tumble rate. So that figured into significantly, and we carried a large uncertainty associated with those environments. On shuttle, the aerodynamic environments are relatively well defined. When we separate from the ET tanks and pull them apart, they're basically outside those shock layers, and we understood that. And of course, we have hundreds of flights, hundreds of SRM experiences, recoveries to understand that. But in our case, it was the aerodynamics that were really driving most of our uncertainty. That, along with we actually had different wind tunnel tests there where we were trying to determine the center of pressure. And again, as I referred to earlier, the center of gravity is largely an analytical term once you're removing the propellant, because the liner burns out or burns away from the inside of the vehicle. So you can't exactly predict how much mass is inside each segment. The other phenomena that's coming into play is slag accumulation within the motor, because we would carry extremes of up to about 3,600 pounds of slag, and that much slag left in the bottom of the vehicle would be enough to shift the CG down to where nose down becomes much more significant. The first point that we started to identify, we actually saw synergy with another problem we had, which was very high vibration loads to the hardware, to the avionics that we were mounting in the aft skirt. So an elegant solution was to add increased mass to the aft skirt. We actually put steel plates down in the aft skirt, mounted them onto the sidewalls. As much as ultimately ended up about 3,600 pounds of increased ballast down there at that point. As we matured in our analyses, we conducted wind tunnel tests. We up at AEDC, up at Tullahoma, Tennessee. We actually conducted a very extensive separation test for our configuration. And so we got a great deal of very good, high quality aerodynamic data that showed us where we expected the wakes, the shock layers to be, and how they would interact with the SRM once the tumbling started. We did some CFD studies looking at, because unlike in the shuttle flies up, burns out, separates, and then just begins to fall back. Well, gravity pulling it down, and it tends to stay in an aerodynamically neutral orientation. You know, it's basically coming down about at a 30-degree angle. That lack of tumbling or any other forces coming in allows the slag to solidify in the bottom of the vehicle. We fire separation motors. We call them booster deacceleration motors. That action forces the slag to slide, which is very viscous material, to basically go up into the center of the vehicle again. And in our CFD analyses, or say ours, really ATK did these detailed studies, basically showed that that slag would get entrained with the flow and flow out through the nozzle. So we went from a nominal of 2,000 pounds of slag to we really expected zero. Again, that shifted the CG in a positive way. There was enough analysis to convince ourselves that was a pretty reasonable assumption. We refined the mass properties with actual values. While I referred to all the segments that don't burn out, we were able to reduce some of the uncertainties near flight because of the non-dynamic, non-propellant segments. We had some very good weight data because we had actual weight data. We actually weighed them before we assembled them. So that allowed us to reduce the uncertainty around our center of gravity. The aerodynamic test probably was the biggest single factor that reduced our uncertainty down enough to reduce the probability of nose down trajectories to be relatively small. I think there's a lesson across the entire program that says when you take heritage hardware that works very well in one configuration, and you change its configuration, you can't just accept all the assumptions, the ground rules, and the analyses that came with that hardware. And this is a really good example of that once you put this in this configuration, you really ended up with a completely different assumptions. The aerodynamics were considerably different than the shuttle. The fact that we were introducing a tumble, and that tumble was introduced to match Ares 1, which is designed to fly higher. Our altitude was the same as shuttles. We essentially got up to about 128,000 feet is where I think our apogee was on the SRBs. On Ares 1, that gets up to more like 170,000 feet. And that difference in altitude is enough that the increased speed during descent would have caused us significant thermal problems, and we'd probably not be able to reuse the SRMs. And so that's what introduced the tumble. And so again, it's a configuration change from the way that we were using it on the shuttle, and resulted in a good bit of analyses and effort to really understand and characterize it well. At the beginning of the program, the Ares 1X program, a decision was made to use the wind tunnel test data from Ares 1. Well, midway, probably a third of the way into the program, we ran into issues that are somewhat related to this nose down effect, but there were significant recovery problems with our configuration because of the way our mass was represented in the vehicle. And so we had to change the separation plane. And so when we changed the separation plane, we essentially invalidated all the aerodynamic data from the separation test from Ares 1. We should have immediately at that point scheduled a wind tunnel test, a unique one like what ultimately we ended up doing. Our hopes were, or our planning at the time when we made that decision, and we recognized it when we made that decision as a possible impact, that we're going to allow the analytical teams, the aerodynamicists, to go off and see if they could reduce the uncertainty with computational fluid dynamics tools and be able to use those and not do the additional wind tunnel test. They couldn't. They weren't confident in reducing the uncertainties with what we had, so we went back to AEDC to do the test. So it was a learning as we went, lesson learned. We probably could have made a judgment call right at that point and scheduled the test, and it would have been available to us sooner. But in hindsight, the data was available in time for flight, and we were successful. I'd have to be a little critical of us in our approach to conservatism. NASA largely is a very conservative organization. I think in reality, especially for a test flight, we started far too conservatively. If we had been more willing to reduce those uncertainties that we were carrying, this problem would have it might have followed a similar path, but it would not have created as much attention as it did. I mean, and ultimately, I think 4%, or I think that's the number we ultimately flew with, that we were predicting could be nose down possibility, was well within the comfort zone of the agency. And if we'd come up with those numbers earlier, there probably would have been less effort. But it's our conservatism that caused this problem to be addressed probably with more resources than we might have been able to get away with.